Hi everyone. As discussed in my earlier video, linear programming is having only a weightage of 6% marks in CBSE board maths examination. They normally ask you a single 6 marker in which they may ask you to formulate and solve a linear programming problem, but sometimes they may ask you one 2 marker and one 4 marker. In that case, they will split the problem into two different problems. In one problem they will asking you to formulate it, and in the other problem they will be asking you to solve it. Keeping that in mind, I have divided this video on linear programming into two parts. One part will be dealing with the formulation and the other part will be dealing with the solution. And the solution mechanism which is covered in your syllabus is only the graphical methods. Graphical method is a method which is used to solve a linear programming when the variables involved are 2 in number. Since the linear programming is having just a weightage of 6%, many times many students omit this topic and they feel that they should not waste their time in doing this linear programming, and instead they should invest their time in those topics which are other more important, maybe calculus, maybe matrices and determinants, maybe probability. But sometimes that appears to be appropriate, but that will cost you 6 marks. To save those 6 marks, in this video I am going to cover almost all the necessary concepts which if you do, you will be able to attempt your question in linear programming in the board examination and hence thereby scoring 100% marks in that particular section. So I'll be doing basic concepts of linear programming and the formulation in one video, and the solution of the linear programming problem which has already been formulated in the first video in the second video. So that way it has been divided into two parts. So now what is a linear programming? Linear programming is a special type of optimization problem. They say it's a special type of optimization problem. Now, what is the meaning of this word optimization? Optimization having the keyword optimize, and optimize simply means best possible. So let us simply reduce, just to understand the concept of linear programming, let's just reduce it to the problem which you have been facing these days. You're appearing in board examinations, and what is your ultimate objective? Your objective is to be able to score very good marks. But can you just score these marks without doing anything, or you have to satisfy certain conditions so that you can achieve this objective of getting the best marks? So what may be the conditions there? Conditions may be that you have to work hard, very hard. You have to you have to study the right material. You have to listen to the right type of lectures. You have not to waste time. So these are the various things which you must satisfy if you want to achieve an objective of a very high score, or the highest score which you can achieve. So this highest of score is your objective, and these are the conditions which are also known as constraints which are to be satisfied. It means you have a set of conditions. You need to satisfy these conditions so that you can achieve your objective. That is what is the meaning of optimization problem. In an optimization problem, you have an objective function which has to be attained subject to certain conditions. So I hope now it should be very clear to you what we mean by this optimization problem. These are a special type of optimization because of the word linearity. Linearity, we all know, you have done a lot of mathematics. The power 2 means you cannot have x1 square plus x2. No, it's not a linear expression. Linear expression is x1 plus 2x2 plus 3x3 type the thing. Means the power of each of the variable, you call it power or you call it degree. Power or degree of each of the variable is 1. So I hope now you know the basic structure of an optimization problem. So you have an objective function subject to certain conditions. Subject to certain conditions. Now objective function, it may be whenever you go to an industry, suppose after doing your graduation or post-graduation or engineering or whatever you do, you will be joining some company. And when you join some company or a production unit, every company or production unit is having an objective. Suppose it is a company, they are manufacturing certain type of products. If they are manufacturing certain type of products, there is a ambition, there is an objective that they want to maximize their profit. But there are certain conditions. If they are manufacturing something, they have to consume the right raw material. They may be using various machines. The machine time is also a condition which is to be satisfied. So that's why we have similar type of situations in industries. Whenever you have to solve a linear programming, the very first step is to be able to formulate it, means write this problem in a proper mathematical format so that it can be easily understood by those people who will be working on this problem. So here I am going to deal with you with some examples. So very first example which I am dealing with you is a problem from the company. It's a prediction type of a problem. If you just look at this, or rather I'll suggest you to take a screenshot of this particular problem so that when I solve it, you can relate it with your problem. In this, a company is producing two different type of products. So it's a product manufacturing unit. One product is needing 1/4 of an hour of assembly work per unit, and another product is needing 1/8 of an hour in quality control work. So it means every product has to undergo two processes. One is the assembly work, another is the quality control work. So if I write this as assembly work, another is quality control work. Along with this, they are also giving you the cost which they will be incurring in raw material for each unit, which is to be 1.2 in the first case, and in the second case it is given to be rupees 1.9. So it is 1.2. So this is something else like this. Here they are talking about the cost, direct cost involvement. But if I'm just considering about the manufacturing of the product, each product is to undergo two processes. One is assembly work and another is the quality control work. They are producing two products. Let this be one product and let this be two product. First product, one unit of first product needs 1/8, 1/4 of an hour of assembly work and 1/8 of a quality control work. Similarly, one unit of the product 2 requires 1/3 of assembly work and 1/3 of the quality control work. Now these process times are also limited and they are given. The first product described as a, okay, we'll come to that later. Given the current availability of staff in the company, each day there is at most a total of 90 hours. So maximum availability of this is 90 hours and maximum availability of this is 80 hours. So it means here we have the conditions. We want to manufacture product. We do not know how many. So it means what actually we want to decide about. We want to decide about number of units of each type of product to be manufactured. We may denote by x1 the number of units of product 1 to be manufactured, and x2 is the number of units of product 2 to be manufactured. And then this is the data which we have to simply formulate. All of you must have done a lot of mathematics. So how will I move with this? So my first condition will be, now if I am talking about use of the first resource, which is my assembly work, 1/4 is used by 1 unit and I am manufacturing x1 units of the product 1. So the total consumption by the product 1 will be 1/4 x1. Similarly, of the assembly work, 1/3 is the consumption by 1 unit of the product 2 and we are manufacturing x2 units of the product 2. So it will be 1/3 x2. And what is the maximum time available? That is the 90 hours. So this would be my first condition pertaining to assembly work. Similarly, we can write it for the quality control work, and I think in the same lines it goes like this: 1/8 x1 plus 1/3 x2 and the maximum is 80. So these are the two conditions which need to be satisfied. But x1 and x2 are the units to be manufactured. Can you manufacture negative units? Either you manufacture or you do not manufacture. So that way you will have to impose two more conditions, because when you are solving it, you have to give a complete structure to the analyzer, to the person who is analyzing this. So you have to impose two more conditions: x1 greater than equal to 0, s2 greater than equal to 0. These are simply called non-negativity conditions, or you may call it non-negativity constraints. And these are your rigid constraints, means these in any case are to be satisfied. You cannot just avoid these. So now it remains to formulate my objective. So I have the set of constraints, I have the non-negativity condition. Now I have simply to write my objective. What is my objective here? I want to maximize my profit. I want to maximize profit. Now let's see how profit is made. What they are saying, if you just look at the problem again, The first product described has a market value of rupees 9 per units, and the second product described has a market value of 8 per unit. So they have given you the selling price. So 1 unit of product 1 can be sold at 9 rupees, but how much are you investing in the raw material of the product 1 per unit? It is rupees 1.2. So your profit is 9 rupees or 9 minus 1.2. Tell me. So it has to be 9 minus 1.2 rupees for 1 unit, and you are manufacturing X1 units. So this is the total profit obtained by selling X1 units of the product 1. Similarly, the profit per unit on the second product is 8, but the investment in the raw material is 1.9 minus 1.9, it's 1.9, sorry, it's 0.9. So it is 0.9 x2. And you want to maximize it, so it is your objective or objective function. It's a mathematical expression, that's why I use the word function, otherwise it's simply an objective. Now let's read out the problem again and see if we have missed something. Further they are saying, what they are saying further, they are saying in addition, the maximum amount of daily sales for the first product is estimated to be 200 units. So they have given one more condition. They are saying you cannot sell more than 200 units of the first product per day. So there is no point in manufacturing more than that rather. So you will just write it as X1 less than equal to 200. Now let's see, do we have some other condition? Do we have some condition on the second product also? But then they are saying, what they are saying, without there being a maximum limit of daily sales for the second product. So no, they're not having any condition on the second product. It was only on the first product. So just go through the problem again and see whether you have formulated it correctly. Okay, so I think 1 by 4 of the first one, that was fine. 1 by 8 of the second one, that was okay. And then 1 by 3 here and 1 by 3 here, not an issue. Minus 0.9, we'll come to that. How many hours? 90 hours. They are saying maximum of 90 hours, it's okay, and maximum of 80 hours, it's again maximum, right? So this is the formulation. Yeah, you do a bit. You may now write your problem as, you may write your linear programming problem as maximize, normally denoted by Z. Z is equal to, what is 9 minus 1.2? 9 minus 1.2 comes out to be 7.8 x1, and 8 minus 0.9 is 7.1 x2. So that is your objective function, and ST is subjective. So what's your first condition? It is 3x1 plus 4x2 less than or equal to 1080, and then you get 3x1 plus 8x2 less than or equal to 1920. X1 is less than or equal to 200. So this is your 1, this is your true, and then comes the non-negativity conditions or non-negativity restrictions. Sometimes we also call these feasibility conditions because they make the problem feasible. So if you want, you can also call them feasibility conditions. So this was the formulation of the linear programming, and I hope you can appreciate and you can realize it was not a tough task. You will just be needing 1 minute or 2 minutes to be able to do this. So that way you can save a lot of time in your board examinations if you just do 1 or 2 examples. So not many examples and you did to be an expert in it. It's such an easy thing as far as your exam is concerned. In industries it may be complicated, it may be tough, but not in an examination. So let us do one more example. Why not to try one more example? So consider this problem. Again, you can take a print out of it. A manufacturer is making 2 types of toys, A and B. So you have 2 types of toys. Means your product here are toys. 3 machines are needed for this purpose. And in time in minutes required for each toy in the machines is given as here. So you are given the time which is needed by each type of toy to be processed on each type of machine. So there is no need to tabulate the data as it is already tabulated by the examiner. Machine 1, 2 and 3 are available for a maximum of 3 hours, 2 hours and 2 hours 30 minutes. The profit on each type of toy A is rupees 50 and that of type B is rupees 60. Formulate the above problem as a linear programming problem and solve it graphically to maximize the profit. In this video we are doing only the formulation part. In the next video I will be doing the solution part, the graphical solution part, which I already told you in the beginning. So let x1 be x1 be the number of toys A to be manufactured, and x2 is the number of toys B to be manufactured. So we are manufacturing two types of toys. But again, there is a limitation on the time. 3 hours of machine A is available, 2 hours of machine 2 is available, and 2 hours 30 minutes of machine 3 is available. But if you just look at this time, the unit here is hours, but unit here is, okay, so but if you look at this, the unit for the consumption is given to be in minutes, whereas the unit for supply is given to be in hours, but there has to be a matching. Either you convert both to the minutes or you convert both to the hours. 1 unit of toy 1, toy A on machine 1 needs 20 minutes. So X units of machine of toy A on machine A would need 20 into X, that is 20X units. For machine 2, tell me, for machine 2 it would be, so toy. So, and similarly 1 unit of toy B on machine 1 requires how much? 10 minutes, and you are manufacturing X2 units, so X2 units will require 10X2 units of time. So the total requirement of machine 1 time is equal to 20x1 plus 10x2, whereas total availability of machine 1 time is 3 hours, that is 3 into 60, that is 180 minutes. Since the consumption is given in minutes, so the supply should also be taken in minutes. What they are saying machine 1 is available for a maximum time of 3 hours. It means you cannot exceed 3 hours. So what should be a constant? What should be a condition? Tell me. Your condition should be 20x1 plus 10x2 is equal to 180, or it should be 20x1 plus 10x2 less than or equal to 180. So just look at this yourself. They are saying 180 minutes of the time is available, but is it necessary to use whole of the time? Or if we say you are having 180 minutes of time available, it means you cannot exceed this. What is more appropriate? You have to use it or you cannot exceed it. So obviously it means you cannot exceed it. It means the maximum available time is 3 hours, means you should not be, your consumption should not be beyond 180 minutes. So this is wrong and this is right. You cannot say I have to consume whole of the time 180 minutes. No, we can only impose the condition that your time consumed should not be more than the time given, which is 180 minutes. So similarly, the second constraint, second condition will be now equal. So is it 10x1 plus 20x2? Second machine is having only availability of 2 hours, so it has 120, and the third is 10x1 plus 30x2, and they are saying 2 hours 30 minutes, so it comes out to be 150 on the same lines. Now are you forgetting something? Is this the complete problem, or are you forgetting something? Yes, you're forgetting the non-negativity conditions, because you have to tell the analyzer, you have to tell the person who will be solving this problem that these constraints can never be negative. Either you produce toys or you do not produce toys, but you can never say that I'll be producing -5 or -10 or -11 units of toys. It's just infeasible, not having any sense. So we have the set of constraints and we also have the set of non-negativity conditions. Now it remains only to write the objective function. So what is my objective here? My objective here is to maximize profit. I want to maximize profit. Now what are the profit? Do I have some data about it? The profit on each type. Yes, they are giving it. The profit on each toy of type A is ₹50. They are specifically giving it. So on 1 unit of toy A, profit is ₹50. I am manufacturing X1 units of type A, so it will be 50X1. Similarly for type B, toy B, it should be 60x2. So am I manufacturing only 2 toys? Yes, I am manufacturing only 2 toys. So that gives me the final version. So finally, how can I write my problem? My problem would be maximize z is equal to 50x1 plus 60x2 subject to 20x1 plus 10x2 less than equal to 180, 10x1 plus 30x2 is less than or equal to 150. Let me see now, 120. So it's 120, and the third one is, I'll have to erase it a bit. So it has to be 120, and the third one is 10x1 plus 30x2 less than or equal to 150, and then x1 is greater than equal to 0, x2 is greater than equal to 0. Sorry, I'm not having any third variable, I'm just having 2 variables. So x3 is nowhere there, it was a mistake. So this is 1, this is 2, and this is 3. Just to revise the things, it's your objective function, these are your constraints, and these are non-negativity constraints. And that's a linear programming formulation. Get full marks. But it was so easy, and I find it to be very, very interesting, and I hope you do the same thing. In the next video, I'll be telling you how to solve it, but since we have already formulated it, why not to discuss 1 or 2 more things, maybe beyond the scope of this video, but otherwise ultimately you need to know it. Now suppose I have to solve it, so first I'll solve 2. All variables solving it would be called solutions. So first of all, I'll be solving this system 2. Whichever ordered pair x1, x2 satisfy this system, whole of this system, those will be called solutions. Then out of these solutions, I'll filter those which will satisfy this. 3. Those will be called feasible solutions. Feasible solutions. So first step, I'll solve 2 to get solutions. From these solutions, I'll filter those which are satisfying 3, I'll call them feasible solutions. And from out of those feasible solutions, the solutions which is maximizing this would be called optimal solution. So now I hope you get a feel of linear programming, which I personally like a lot. And I hope you will also start liking it. You must have started liking it, or you'll be liking it a lot. And you'll need this lot in all of your life, whenever you proceed ahead as an engineer or a big professional. So that finishes my formulation part of linear programming. So you will find the remaining things in my subsequent video on linear programming. So in this video, we covered the various necessary concepts of the linear programming along with how to formulate the linear programming, which forms an important part of your examination question in the board. In the subsequent video, you'll find how to solve that graphical, which is another important part which you'll be considering with this. But with this video, I hope you would be able to get those 6 marks in your CBSE 12th class board examinations. All the best. See you soon. Thank you.